there is somebody named root in there, and if I say root funky character hyphen hyphen, then we get a valid cookie back. And if we were to go say print info on that person, it was 1001, I believe. Then yes, indeed, my concocted application says that it's root. Now the application does one really stupid thing, just for demo purposes. When it takes the Unicode string, it explicitly converts it to Windows 1252 using the default .NET application encoding mechanism. And you can see I have put a big comment there that says dumb. Now the one thing is you'd say, who would possibly do this? Well, nobody will possibly do this in this one very limited example, but you will see this when it crosses machine boundaries. Let's say this wasn't my local database; it was on my machine that was built to run with the application server, built to run with .NET. And let's say it's some other MySQL server. It's on another machine. The machine is running a different locale, and it has to do some sort of conversion in order to make that work. You're going to see things like that. I have seen things like that. I wish I could have demoed them, but can't. Any questions about the foundation of that attack? Under what circumstances it can occur? Okay. I'm sorry, I can barely hear you back there. Oh, well, for demo purposes, I didn't want to start pointing out raw HP posters. What you could do is if you were using WebScarab or any other web proxy, or if you're just typing things in a netcat, you could just simply encode the UTF-8 encoding of it, which I forgot off the top of my head, but you basically convert Unicode 2032 to UTF-8, put percents before it, and then send it off. I actually have a tool in a demo in a little bit here that does that. For this particular demo here, the way I got that character was to just open up car map and say go to 2032 and copy and paste it. All right. So that's the big attack pattern you see when you're starting in Unicode and you're going to a locale-specific text. There are other attack patterns in the reverse direction. So I get something that's locale-specific, I convert to Unicode, and then I do something interesting with it, like access a database. The attack pattern here is eating characters. So we talked about UTF-8 and shift-gist that have these lead bytes in them. And these lead bytes don't mean anything of them by themselves, but any parser is going to interpret them in the context of what runs after it. So if I send somebody a character like, well, to go back to the shift-gist example, if a parser were to look at hex 8260, then they were to do that, look up through the code pages that I illustrated earlier, that would be equivalent to the Unicode code point FF21, which is the full width Latin capital letter A. So there's another funky character that corresponds to something in the alphabet that might be misused by people. There's plenty more like that, but that is how the lead byte and everything occurs there. Now, if I say 8227, that's not mapped to anything. If I were to go back and look through those code pages, I'd see, okay, hey, here's the trail byte page for lead byte 82, and I look, and 27 would be unmapped. So that, when you'd convert it, would become error. It would usually become whatever the default character is, and that's going to be like a question mark. If I put in hex 822727, nothing with an apostrophe, that will become, so like I said, that'll convert from 8227, will become unmapped, become question mark, and it'll be followed up with a 27. So where is this interesting? Well, let's say when I get my locale-specific text, I perform validation on there. I look for apostrophes. I go through and say, okay, here's 8227. Oh, there's an apostrophe. Double it up, 8222 or 822727, and then I send it on back to the database routine, which encodes it into Unicode and then accesses the database. Then all of a sudden, I become, whatever it was becomes blah question mark, which is the 8227, and then the apostrophe that was put in there to double up, and then it goes on from there. Now this is one example from shift-gist. You could do the same thing with anything that stupidly eats characters within the parser. If I were to put C027 and something said, hey, this is UTF-8 lead byte and then the trail byte, and I go through and I escape out the 27 and then the C027 comes out, same thing would happen. This is particularly devastating against anything that escapes or doubles up characters in order to make them clean. Any questions about that? All right, well, I don't have a demo on that one. The next one is foiling canonicalization. So a few minutes ago we talked about how UTF-8 had non-minimal encodings that were explicitly banned by the Unicode Standards Committee as being not compliant if you do it. And the example we gave was C08E, which is a non-minimal encoding for hex 2E, which is a period. Now that left all the system implementers to decide what do we do when we come across one of these. And what most people do, actually without exception the ones I've looked at, is they simply drop the character. Well, why do you drop the character? Well, sending up an error every time you have a converted character go wrong is going to cause all kinds of problems. It's something that you don't want to throw an exception up or every database in the world will die. I mean, it's something where you pretty much have to detect and fix it. So in order to have something, still work, they just simply drop the character. And so where is this interesting? Well, if you're foiling canonicalization once again, go back into the website example. We have the web folder / index.html. We can't get by on .. to kick us out. But then we do .non-minimal encoding, .. non-minimal encoding, / blah. Now, if something looks at that and is looking explicitly for .. or anything along those lines, they're going to kick it out, but they're going to see here not there, and so they're going to allow it to keep going. Now, when that gets converted by the UTF-8 parser, it is going to be dropped, and so what comes out the other end? .. / and then a demo that shows this happens but doesn't have any specific security issue. Is to log in. Now, for those of you that are really up close or have very good eyes, there is a way to use this application which is based on get parameters, and I wish I had a bigger font here, but I have to do encodings which are escaped out by the form submission method. But anyway, if I click on this, it's the same login user, sends in my name and password, and I get the same success string. So, my password is here at the end, it's still $COTT, but if I put in %C0, %AE, then that should be a period, or a non-minimal period, or something, a question mark inside the middle of my password. That should kick it out. Oops, and it did. Had a typo in there. Oh, thanks. Okay, so there we go. %C0, %AE in the middle of Scott, and that comes back valid. It dropped the non-minimal encoding, still let everything go through, and this would be of extreme interest in trying to bypass any canonicalization protections. Any questions? I left more time for, whoops. So a third attack pattern, I'm sorry I don't have a demo for this one either, but it's mistaken identity. Now many of the code pages that have been designed, this goes to your question a moment ago, many of the code pages have been designed to be ASCII compatible. So that if I have a single byte that is from the old alphabet, it kind of looks like what we are used to. An A still looks like hex 41, or maybe 0 extended hex 41, like in UTF-16. And a lot of validators have taken this advantage of this of this similarity. So if I'm creating a validator that's looking for cross-site scripting, I can just go through and look for hex 00 3E script, hex 00 3F or whatever it is. And that's a very useful thing. But there are other encodings for Unicode that we talked about that aren't ASCII compatible, like UTF-7. It actually is ASCII compatible, but it doesn't have to be. Basically, it's a 7-bit encoding scheme designed for things like mail transfer. And what you can do with it is, if it's an A, you can still put an A, but if it gets outside of the known safe characters, you're supposed to base 64 encode it, more or less modify, and add a plus and minus on the end of each one. Now, there's nothing that says you can't do the same thing with a script tag or an apostrophe or anything else that's deemed safe. And actually, this was a flaw that hit Google with the cross-site scripting not too long ago, where he took a script tag, UTF-7, that sent it up there. The validating routine just saw a bunch of standard characters, A, B, C, whatever. Didn't think that it was anything malicious, so let it pass on through. When it got back over to the browser recognized that it was UTF-7, decoded it, and displayed it. Recently on BugTrack, there's been a lot of discussion about what 7-bit ASCII should be interpreted as. ASCII is a 7-bit encoding scheme. Computers don't chomp on 7 bits, they chomp on 8, at least. And so what happens to that, the most significant bit, well, ideally, you should ignore it. A lot of people just simply zero extend it. It becomes, you know, hex 00 through hex 7F. But ideally, by the standard, that top bit doesn't matter. So you can simply put a bit on there. Hex 27 becomes hex 87 or A7, and if you put that in there and it actually interprets it as proper ASCII, it will become apostrophe and go through to your database, or same thing with script tags or anything else. Other things like that, EBC DIC doesn't look like it. UTF-7 and ASCII are the other two big ones. Any questions about that? All right. So here's the bonus. So we talked a whole lot about character encodings. At a basic level, that's where most of the data is, but we talked earlier about how internationalization includes a lot of things, or locale-specific preferences, timestamps, and sort orders, and currency symbols, dollar versus euro, and all that other good stuff. So the timestamp attack, today is August the 2nd, 2006. So if I have a timestamp of 08/02/06, that could be August 2nd, 2006, or February 6th, 2008, depending on how you interpret that string. So if you have a ticket expiration, which is persisted into a string rather than a computer time, and you send that across machines, very interested in like brokered authentication schemes, and that machine is of a different locale and interprets that string differently, then all of a sudden you have a ticket expiration that occurs 2 years in the future, not right now. Sorting attacks, this one's kind of interesting. So which comes first in general, Apple or aardvark? Aardvark has 2 A's, so it'll come before Apple. But if you go in Dutch, AA is a lowercase version of a character that's far later in the alphabet, so it actually comes pretty close to the end of the alphabet. So if you're building a sorted list for integrity checking or something along those lines, then and you interpret that on Dutch, it's going to be pretty bad. Same thing with what is your proper decimal separator? Sometimes it's period, sometimes in other locales it's going to be a comma. If you persist your data into a CSV format, then your bank is going to be very unhappy when all of a sudden you can manipulate that format. So there's a couple other things to think about, though character encoding is typically the attack that is most worthwhile. So in support of all this, are there any questions along those lines? Okay. Yep.
So in all those Unicode pages, do the Unicode pages themselves say what the proper order of characters are as they sort?
Yeah.
Can I look up in Dutch is represented in ISO, right?
Mm-hmm. Yeah, so there's Unicode specified sort orders and locale specific stuff like that, and same thing with the different ANSI code pages. Anything that's...
If you have a sort function that understands Unicode, then it should go like that.
Mm-hmm.
You can audit for text, but maybe it was intended.
Yeah, definitely. So testing all these equivalent characters, eating characters, things like that is very difficult, and so I've recently written a tool that has taken right now a bunch of equivalent characters to core ASCII characters which usually cause problems, things like apostrophes, quotation marks, brackets, parentheses, and we'll then take an arbitrary HTTP post or GET, manipulate all the parameters, and see if it can find issues, kind of like the one we discussed earlier. Call it I18N attack, which is I18N is internationalization shorthand, and I'll give you a quick demo of it right now. So the way it works is it takes, it'll look for properly formatted HTTP requests inside of a general folder. You can use it with WebScarab. How WebScarab will persist all of your HTTP requests, put it in a single folder. You can just point at that, go through and read those requests, and then identify the parameters, and then start working against them on with a XML database.